It's a great pleasure today to welcome Dr. Emily Sena to our Miami Project lecture series. Dr. Sena is currently a senior lecturer at the University of Edinburgh, where she's made her home for the past 20 years. Senior lecturer is one of those things that can't readily be translated, so I'm not going to try, but it's certainly a faculty position, kind of like an associate professor. Dr. Sena received her training largely from the University of Edinburgh herself, earning a BS degree, and I note that she was smart enough to study pharmacology for this degree, for which I applaud her, and then took a Ph.D. in clinical neuroscience doing stroke research. The latter somehow involved a stay in Australia, which is certainly a nice perk. That something didn't happen to me. Since the start of her professional career, Dr. Sena's work has focused on the science of research reproducibility. This so-called meta-research is an evidence-based effort to uncover factors that affect experimental rigor and reproducibility, and therefore improve the likelihood that the kind of preclinical research that we do in the Miami Project, for example, can be effectively translated to a clinical setting. To be a bit parochial, this issue is a particular interest of our own lab, as Vance and I have been involved in reproducibility efforts in spinal cord injury research for the past 8 or 9 years. He can correct me if I'm wrong about that. The studies that Emily and her colleagues have done have been used to inform guidelines for good laboratory practice, and their group has collaborated with scientific journals in an effort to improve research reporting. Emily is the current convener of the Camarades group, which was originally founded, as you probably know, by Malcolm McLeod and David Howells, to understand and try to address failures of preclinical translation, which had become evident by the time this group began its work. And she is an author on the recently updated ARRIVE guidelines that are for animal research reporting. In her spare time, she now convenes her university's race equality and anti-racist subcommittee, so she's not wanting for things to do. And it's worth noting that she's an author on a paper that has more than 2,300 citations, which I, for example, am not. Emily, welcome to the virtual University of Miami. The floor is yours.
Thank you very much for that very kind introduction. I have to admit, I'd rather be in the real Miami than a virtual one, but it's still very much an honor to be here today to share a bit about the research that we've been doing and hopefully convince you that some of the things that I think are important are indeed important. So the title of my talk today is Reproducibility to Translation, Some Factors to Consider. I will start with disclosures. These are mine. I'm editor-in-chief of BMJ Open Science and also a co-founder of an initiative called PCI Registered Reports that I'll talk a bit about later. But I think probably more importantly, what the research I'm going to talk about today is, you know, what I do in my day job and, you know, pays my mortgage and pays for holidays and things. So I'm clearly invested in, like I say, convincing you that it's important. So John covered this a little bit, but I also wanted to get across the perspective with which I come to this work. So I describe myself now as a preclinical meta-research scientist. So essentially, I'm interested in the modeling of human diseases in the laboratory, in their rigor and reproducibility. And I come to this in a meta-research space. So I research the research itself, try to bring evidence-based recommendations about how we could improve the quality of the research that we do. And our group came into this work with the hypotheses that in the life sciences, there are a number of perverse incentives. We want to get our research published, we want to get research funding, we go for academic promotions, which pushes us to produce positive results with maybe slightly less attention to how valid those results are. And then when we think about the use of animal disease models, they are additional pressures to reduce the number of animals that we use in our experiments because of things like the cost, how long the experiments take, ethical considerations and feasibility that results in studies either being underpowered or of unknown power. And together, I think these factors can compromise the utility of animal models and contribute to translational failure. And just to be clear, what I mean by translational failure, our work started in stroke research. I think stroke kind of became the poster child for translational failure, but I think it's a phenomenon that's common across lots of different disciplines. And these are some data published by colleagues in Australia, in which they identified over 1,000 different interventions that have been tested in a laboratory model of stroke. 600 of these were tested in an animal model. 374 were shown to be effective in these models. Just under 100 would take... Oh, is there somebody asking a question there? Just a flip. Just under 100 were taken forward to be tested in a clinical trial. And only one of these interventions, clot busting treatment with thrombolysis, was shown to be effective in clinical trials. There are some additional interventions that are used clinically but don't have that same supporting underlying preclinical evidence. And to be honest, showing the data like this is slightly disingenuous, because it's not that, you know, the interventions flowed through this pipeline to end up in a clinical trial. But actually, I think for thrombolysis and stroke, it was evidence from myocardial infarction trials that then led to the design of the stroke TPA trial. But it's not just stroke. There's been lots of examples presented in other domains: MS, pain, hemorrhagic stroke, and Alzheimer's disease have all spent quite a lot of time describing the issues around translation. But I think if we take a step back and not just think about translation, but think about replication, so not thinking about how we translate what we see from a preclinical setting into a clinical setting, but just the ability to replicate findings in a similar setting, there are also additional problems. So these are examples of some retrospective studies that were published by pharmaceutical companies who were sharing their historical experiences of attempting to replicate published academic findings. The two main papers that have been published describing this phenomena were by representatives from Bayer and Amgen, who both describe substantial issues in replicating what they observed in the published literature. But I think it's important, and I think this caused there was lots of conversation around this, and there was lots of focus on these two studies. But I think it's important to be reminded that there's almost certainly a selection bias here. These are two companies that have presented their data out of who knows how many companies have attempted to publish academic findings, and also a recall bias. Bayer and Amgen have presented data on 67 and 53 replication attempts, but we don't know how many replication attempts they have. And also, one thing they didn't do is make the details and the data available behind their replication attempts. So we don't know with how much validity or how much fidelity even to the original experiments their replication attempts had. But there have also been some prospective replication attempts. These are academic-led studies with lots of attention paid to the faithfulness of the original study design. They were adequately powered. They pre-registered the study. And again, we still see some issues with translation, although the majority of these aren't in the life sciences. Again, I think there's selection bias in this data set. But I think more importantly, and I think what they did to set a good precedent, was make all the details and the data available behind these attempts. So I think that was me trying to describe, I guess, the scale of the problem. And there's a number of potential sources of bias that I think contribute to our inability to replicate and translate preclinical findings. The first is the internal validity of the study, so the strength of the cause-effect relationship. Are we seeing other outcomes we're observing because of the intervention that we've delivered in an experiment, or is it because of some sort of other unknown source of bias? And things that you can do to strengthen the internal validity of an experiment are things that, replicate randomization, blinding, using appropriate controls, for example. External validity is the generalizability of a research finding. So the conclusions that we observe in an experiment, does it generalize to other species or a different time, or importantly, patients in a clinical setting? Construct validity. So essentially, are we measuring what we think we're measuring? And this really boils down into the models that we're using. So what are the aspects, rats aren't mini humans, what are the aspects of the human disease that we're capturing in our models? And then the outcome measures that we use. So in stroke research, in the preclinical studies, we often measure infarct volume. But clinically, we're more interested in daily life and function. So understanding what the constructs that we're looking at, clearly very important for translation. And then reporting bias, or reporting biases. And publication bias is probably the most talked about reporting bias, so the phenomena that not all research findings are made available. But biases aren't just a science problem. I think it's important for us to reflect and remember that, we are human beings. Human beings are designing and conducting research studies. And I always give this example to demonstrate that biases are a part of human nature. For those of you who are interested, particularly in classical music, you might know who Zuba Mehta is. He was conductor of the LA Symphony and the New York Philharmonic between the mid-60s and the early 90s. And he's credited with saying that he just didn't think women should be in the orchestra. He thought they didn't have the skills. He thought they didn't have the stamina to participate in these prestigious orchestras. And then in the 80s, blinded auditions were introduced. So instead of standing up in front of the conductor and playing whatever instrument it was that you were playing, you auditioned behind a curtain. So the conductor wouldn't know whether you were a woman or a man or any other protected characteristic. And they think that blinded auditions account for about 30% of the increase in the female proportion of new hires at major symphony orchestras in the US. But going back to the science, unfortunately, biases are prevalent, and I think they're important. So in the context of a number of systematic reviews that we've done over the years to try and understand some reasons behind translational failure, we've looked at the reporting of certain measures to reduce risks of bias. And in this table, I'm just presenting two: the reporting of randomization and blinding the assessment of outcome. And we see across different disease models, stroke, spinal cord injury, Alzheimer's, Parkinson's, EAE, the model of stroke, and glioma, very few studies report randomization, and few studies report blinding assessment of outcome. Although I have to say, spinal cord injury is definitely up there in terms of more likely to be blinded than other disease areas. And then we've also looked at the impact of not reporting these measures to reduce risks of bias. So these are data from one of our meta-analyses. So we've collated all the studies that answer a specific research question, and pulled together the effect sizes from each study, and we get this overall estimate of effect. This grey bar behind here is the overall estimate of how effective this intervention is in the disease model that we're looking at. And then we stratify the data according to those that do report versus those that don't report randomization. And we see that the studies that do report it report much smaller treatment effects than those that don't. But these data have all been collected in the context of trying to understand where things have gone wrong, where things haven't translated from a preclinical to a clinical setting. And one of the comments that we often got from, or often have received from people is, well, you're looking at everything. Some people do good experiments, some people do bad experiments, and you're just lumping everything together. And actually what you want to do is look at the good quality journals. If you look at good quality journals, that's where you'll find the good quality research. And I say quality because I think the interpretation of what quality means is different to different people. But I think when people say good quality journals, they're trying to say high impact factor journals. So, the single name journals, single word journal names. And what we've done is for each of our studies in our data set, we've ranked them according to decile of impact factor. So these up here are the high impact factor journals, and these are the lower impact factor journals. And then we've looked at the reporting. We've got the 95% confidence intervals, which is what these lighter lines are, of randomization, blinding assessment of outcome, reporting a sample size calculation, and a conflict of interest statement. And this actually is significant in terms of high impact factor journals are less likely to report randomization. This is just, there's no difference. It doesn't matter where you publish. Nobody reports, or very few people report blind assessment of outcome. Nobody reports the sample size calculation. But you're more likely to report conflict of interest statement in a high impact factor journal. And then people say, yes, but people can get into these high impact factor journals. What you want to do is look at the good quality institutions. So the best institutions are the ones who have a culture around producing high quality, rigorous research. So we did an exercise where we looked at the best institutions, and these are from the UK institutions. We've anonymized them because we don't want to create too many enemies. And these top 5 UK institutions are determined through this painful exercise that we have to go through in the UK, which essentially the UK government allocates additional funding depending on how impactful and what your status in terms of qualities of your institution. And every university gets ranked, and then the top ones basically get more money to continue what they're doing. So this was an exercise that was done in 2008, and we took these top 5 institutions. We then looked at all of their preclinical studies, so any in vivo publication they have in 2009 and 10, looked at those papers and extracted the information for those in vivo studies, whether they reported randomization, blinding, and inclusion-exclusion criteria, and the sample size calculation. You see the y-axis here only goes up to 30%. So very few studies report any of these measures to reduce the risk of bias. Only one study, and I will name it because they've done well here, the University of Oxford, reported all 4 of these measures to reduce risk of bias in over 1,100 papers in this data set. But a lot of these assessments that we've done, I think are getting old, and I think things are improving. So these are data from a review that we did looking at the intervention interleukin-1 receptor antagonist for experimental stroke that we published in 2009. And we see, again, very few studies report these measures to reduce risks of bias. And I happen to know I developed a relationship with one of the lead professors in this interleukin-1 receptor antagonist space. And I think it must have been maybe in 2013, 14, we were sat next to each other at a conference and we got talking about this paper. And he said to me, you know, we were really, really irritated when that paper came out, because they had done 90% of the papers in the systematic review. And I think they saw it as a somewhat unsolicited attack on their research and how they were conducting and reporting their research. They actually published a rebuttal to our systematic review. And he says, but despite that, what we realized in response to your systematic review is that even though we were doing things, because they claim that not reported didn't mean not done, even though they were doing things, they weren't reporting them. So then they got these low scores in our reviews. What they need to do is start reporting it. And that's what he said they had done. So I said, oh, that's interesting. I'll do an update review. So we conducted and published an updated review in 2016. And you can see the huge improvement in the quality of reporting of measures to reduce the risks of bias in this data set. So moving on to external validity. So this is the generalizability of research findings. And I've got a colleague in Switzerland who spent a lot of time investigating the standardization fallacy. And essentially what he is talking about is our efforts to increase reproducibility by reducing variation. And we do this by standardizing things like the lab environment, the tests that we use, the genetics of the animals. Actually, what we're doing is we're just increasing our risk of detecting effects with very low external validity. So we're seeing effects that only work in that very narrow circumstance. You know, it's only when that specific postdoc does that experiment, that time of day, when there's no noise and the temperature's at a certain degree, that we can replicate that finding. And he talks about the reaction norm. So if we think that the phenotype that we observe is an interaction of the environment and the genotype of an animal, then there's a range in which you observe a reaction norm. And then depending on what other nuisance variables are around, and that might be the level of light, or it might be the radio being on, or the perfume that someone's wearing, you might observe an effect here, or another variable, you might observe an effect here. And then we characterize this as a reproducibility failure. You know, we've failed to replicate our findings, but actually what we may be doing is sampling different areas of the reaction norm. And we did some simulation work to look at how we could address this and improve reproducibility, looking at multi-center studies. So and I'm going to focus on 1 lab versus 4 lab studies. So in the 1 lab example, so the dotted line here is the true effect with a 95% confidence interval. And when a study is done in 1 lab, because of these, I think, these nuisance variables, some of the experiments don't overlap with the confidence interval of, I said the true effect, I meant the overall effect, don't overlap with the overall effect. And then it looks like we've got reproducibility failure. But when you get 4 labs to do the same experiment together, and then you pull their findings to an individual effect size, we see that every single one of these experiments overlaps with the overall effect that we're observing, suggesting better reproducibility. I mentioned reporting biases. So this, like I say, is a phenomenon that not all outcomes and a priori analyses are reported. Publication bias is, I think, is the most well-known reporting bias. We're neutral, and I've underlined the word negative because I think it's unnecessarily pejorative. I think, and it goes back to my earlier slide where I talked about our incentive structure to push for producing positive results. But I think understanding what doesn't work, accepting the null hypothesis is part of our scientific endeavour. And I think, important questions, well-designed experiments, they give us a robust negative finding, I think should be rewarded. But unfortunately, our culture doesn't currently support this. So they take longer to get published, or they just don't get published, so then they're less likely to be identified. And you can imagine that, if 10 people all do the same experiment and just by chance one gets a positive finding and that only one is the one that ends up being published because it's positive, it then skews and slows our progression. We've also got selective analysis, which, to put it bluntly, I guess, is simply repeating different analyses until you get your p is less than 0.05. Whether or not that analysis is the most appropriate for the data set and the research question being asked. And selective outcome reporting, that is something that I think affects us in preclinical research, because I think it's quite common to look at multiple outcomes in an experiment, but then only the outcome that reaches your p is less than 0.05 is the one that ends up in the public domain. And we looked at publication bias. You can see this is an old paper, but it's got the old PLOS logo. But we looked at publication bias in stroke research, and using a technique called a funnel plot, where you plot on the x-axis the effect size from each experiment. On the y-axis, you've got the precision, which is the inverse of the standard error. So the narrower your error bars are, the more precise the study is. And what you expect with no publication bias is that the more precise studies should lie around the true effect. And as you become less precise, you should have an equal distribution of positive and negative studies. And the black dots are from our data set. And we see we have a lack of imprecise negative studies. We then use a technique called trim and fill, which essentially tries to make your funnel plot more symmetrical and imputes these theoretically missing studies, and then adjust your effect size, taking these into account, which are these red dots here that have been imputed by the trim and fill formula. And in this data set, it looks like, our overall effect went from 32% down to 26%. And it looks like about 1 in 6 experiment remains unpublished. Now, I think this is a gross underestimation of how big this problem is, mainly because a lot of these experiments on the negative side of the funnel plot weren't truly negative publications. They were publications that had multiple experiments in them. Some were positive and then some were negative. I think only 2% of our data set were truly negative. So I think all of that 25 minutes of preamble was me trying to convince you that the reproducibility, replicability, and reliability of biomedical research is under threat. And I think if research results aren't replicable, then our scientific progress is stalled. We can't translate our findings into clinical applications. I said here time and money are wasted, but I think lots of resources are wasted, including the use of animals in the research that we do. I think there's a real risk to public trust in research. I don't know if you have the same phenomena in the States as we have in the UK, where somebody, a big finding happens and a paper gets press released and it ends up in the news saying scientists from the University of X have discovered a cure for Alzheimer's disease. They often don't say that the study was in mice. And these reports have come out regularly, but people aren't seeing effective treatments clinically when their loved ones are afflicted with these disorders. So I think there's something very important about ensuring that what we disseminate is as close to truth as possible. And I think also capable and talented early career researchers start to become a bit disillusioned with the field, and I think it means that we start to lose great talent in academia. So ideally, I think studies would benefit from a range of tools that help or that facilitate robust design in experiments, i.e. strengthen the internal validity or the robustness of the study, that support collaborative studies to strengthen external validity, that support clarity of how studies were performed so that we can assess the robustness and replication, that confirm that studies report what they set out to do, to minimize reporting biases, and that also allow us to access data so that it can be used and compared efficiently, again, so that we can assess the robustness and replication. So what I'm going to do now is quickly, I think I've got about a slide for each of these points, just describing some of the available tools that are out there to support these endeavours. So for robust design, they are things like the EDA, which is the Experimental Designer System. This is a free online tool that was developed by the NC3Rs. I don't know if the NC3Rs are known in the States or not. They're essentially a body of a government body that are tasked with developing resources and tools to support the rigor of animal research. 3Rs is very much is their key theme. So reduction, replacement, and refinement. And this, I guess, comes under the refinement aspect. It's a tool to help ensure that you use the most appropriate number of animals. It supports in reducing biases. It can randomize for you, ensures that you're using the appropriate statistical analysis, etc. Any statistician that I speak to always says, when scientists come to the end of their experiment with their data, asking how to analyze it, it's far too late. All they can do is essentially give you a post-mortem of what's gone wrong. What you want to do is get statistical input and advice at the beginning, at the design stages. And something that's maybe slightly, I guess, novel is peer review, which you can get using a format of publication called a registered report. So you develop your idea, you design it, you essentially write the introduction and methods, and you submit that to a journal for peer review before you've done any data collection. And essentially it allows you to get peer review input at a stage in an experiment where it can have the most effect, when it's most useful. You then go through your revisions and you get in-principle acceptance, where the journal commits to publish your study irrespective of what the findings are. So it also changes the incentive and the pressure, because then it becomes about following your methodology rather than getting a result. And then you do the experiment, you collect the data, you write up the paper, you add your results and your discussion, and then the stage 2 peer review is essentially making sure that you did what you said you were going to do. And for preclinical research, we offer this at BMJ Open Science, but it's also offered at an initiative that I'm involved in called Peer Community In, which is a non-profit. So Peer Community In is a non-profit, non-commercial platform that publishes peer reviews of preprints. And what happens is when you go through the peer review process at PCI, Peer Community In, journals then can either, once you finish the study, can either bid on your accepted article. There's a number of journals that have signed up to overlay Peer Community In. So as long as you're within their remit and their scope, you won't have to go through additional layers of peer review. And that's got the utility that it then allows you to choose journals at the end of your study, rather than having to, with registered reports, choose a journal before you started the experiment. But like I say, registered reports emphasize the importance of the research question and the quality of the methodology, and try to get around some of these biases that are common. Collaborative studies. I led a group a few years ago called Multipart. that sought to try and define the key facets of multi-center preclinical studies, informed by how they do multi-center clinical trials, but focusing on some of the, I guess, the issues that are specific to animal studies. I think a real benefit of multi-center preclinical studies are that it can improve some constructability, because then, you know, some people only do a certain model in their lab or have access to certain outcome measures. But by, you know, working with lots of, you know, with your with colleagues in different labs with different models, you can increase that kind of coverage. But my advice is don't ever try and do it on the cheap, because we tried this and thinking that we could kind of get around some of these things, but actually having specific funding to support multi-center studies is, in the same way that clinical trials do, I think is important and paramount. Also being clear on who did what. If there's one take home today, it will be get an ORCID ID. This is a unique identifier for each researcher. It takes about 30 seconds to get an ORCID ID. Yeah, please do that. We can ask questions. If people aren't familiar with ORCID, we can talk about that afterwards. I'm a big fan of the credit taxonomy. I think this whole focus on first and last authors it doesn't help science. I would love for us to credit science in the same way they do film credits. Just say what people did, because people have very fundamental, important roles that ensure that an experiment or study can happen, and without them, it wouldn't happen. But our emphasis on first and last authors, I think, don't help. So the credit taxonomy is a high-level taxonomy with 14 contributor roles to try and get around that. Clarity on what was done. John mentioned the ARRIVE guidelines. There's a new iteration of ARRIVE that came out recently that are reporting guidelines for animal experiments. But there's lots of other initiatives as well. I'm a big fan of protocols.io. So in a paper, you can't, you know, you're not writing SOPs in the methods section, but having those SOPs, I think, are important for people who want to replicate a study. And protocols.io is a platform that allows to have those detailed SOPs. They're generally living documents, but, you know, once you've finalized one, you can timestamp it, it gets a DOI, and that DOI can be linked into a paper. So if somebody wants to get into a deep dive of what was done in your study, they can do. Electronic lab notebooks. I think there's great utility in them, although I think getting people to actually use them is one of the great difficulties that people seem to have. And the resource identification initiative, again, it's these IDs for specific resources. They're unique. So there's a great example of somebody who was trying to replicate a study, and it turned out that they bought their antibodies from one company and another company. They did it slightly differently, but the antibody had the same name, and just not knowing the unique identification of what it was. And it took a long time for it to figure out. I think RIDs are also very useful. Confirmation of what people set out to do. Trial registries. You know, if you do a clinical trial now, it's really difficult to publish it without registering it first. I don't think every single animal study should be registered, but I think there's, especially confirmatory studies, you know, in hypothesis testing experiments, I think there's a place for registering them. There's now platforms to allow you to do this for preclinical research, preclinicaltrials.eu. The German Federal Institute for Risk Assessment developed an animal registry. These are all open internationally, they're not just European. The Open Science Framework is domain agnostic, but allows you to pre-register a study. Publishing study protocols is becoming much more common as well. And of course, voted reports. Access to data so that it can be used and compared efficiently. I'm a big fan of preprints, getting data out there quickly. We did a study in Edinburgh where we looked at the time from approval to do an animal experiment to when it's published. And it's about, I think it's nearly 3 years, but 25% of that time is spent at the journal, which, I think again slows down progress. And if you have a publication that you're submitting, I think making it available on a preprint server can help. And things like bioRxiv, you can update it with every revision. I think it supports open peer review and transparency. Making data available, there's lots and lots of platforms now. Ones that are general, but there's also domain-specific platforms that are available to share data. A lot of journals have got open data policies, which I think has unfortunately led to undocumented data dumps. So people say, I've got to make my data available, and they just stick it somewhere, and there's no quality control. They're often not linked to the original study very well, and you've got no idea how you'd even begin to decipher or reanalyze those data sets. Sorry. So making data fair, findable, accessible, interoperable, and reusable, I think is also very important. So that was a kind of whistle-stop tour of some tools that are available. And some of you may have noticed that not all of them, but a lot of the tools that I talked about were rooted in open science. And I wanted just to give a quick plug for open science. I think there are lots of benefits to open science. I think for science itself, it improves transparency of the research. It makes it more verifiable, efficient, reproducible, and sustainable. I think for society, I think we need to remember that we don't just do science for ourselves. We do it for society as well. And I think it's important, partly around this issue around public trust in the research that we do, that the public can gain access and use scientific information. And I'm sure there's lots of people who wouldn't, but there's something in knowing that you can if you want to, that I think just, I guess, increases your trust in something. But there's also selfish reasons as researchers. There's studies that have shown that open research gets more citations, it's obviously more visible, associated with increased rigor and transparency, better documentation. And I think it's also more equitable, because I think it then starts to reduce or takes away the barriers from some of the gatekeepers for science, which I think is important. But it would be remiss for me not to acknowledge that they are obstacles. I think in our reward and incentive structure that we have in academia, it doesn't support open science. Well, not yet, but I think that's the direction that we're going in, at least here in the UK. But yeah, I think there's still some way to go. I also showed this slide. I think it's great. It's the open workflow, the open science rainbow, that shows that throughout the research life cycle, there's lots and lots of opportunity to increase the openness and transparency of the research that we do. And there's also people who are interested in engaging in more open research. The Reproducibility for Everyone initiative has some great resources to support people in that endeavour. Oh, excuse me. And in the UK, we've got the UK Reproducibility Network. That's a grassroots organisation that has a huge amount of resource and support now. And they've supported networks that other countries develop to, like I say, share resources, do a bit of lobbying, put pressure on institutions to support reproducible practices. And I guess one of the things that's come up quite a lot, and I really like this graphic, it's from a Nature article that some colleagues of mine wrote, where they talk about whose responsibility it is to uphold robust science. So we've got different stakeholders here: funders, journals, researchers, and institutions. And actually, funders and journals seem to, have a lot of initiatives and providing a lot of support to try and make research robust. And there's a number of researchers who are also engaged. But I think institutions, and I think this is largely rooted in our reward and incentive structure, and maybe aren't quite holding up their end of their end of what should be done just yet. So when thinking about, I've called this improving a research culture, but you could even just changing a research culture. There are different steps. I borrowed this from Brian Nozak from Open Science Framework, where he talks about, first you need to make it possible, and that's really about creating the tools. And I think we do now have lots of tools, that the innovators have come up with and have developed. You need to make it easy, so that you get that kind of early adoption. And I think for certain open science practices or reproducible practices, this is where we are. For others, I think we've made it normative. Start changing the value structure. I think this is when you get the early majority on board. When you make it rewarding, I think that's when you start to get that late majority. But it's unlikely that you'll get everyone without policies. You make it required, and that's when you get the laggards kicking and screaming to do these things. And I think to a large degree, I think this is very true. And I think that's where a lot of open science and reproducible science activity has been focused. But I think sometimes something that's missing is really assessing, do these good ideas actually work? There's lots of good ideas, and I showed you lots of different tools that theoretically we think will improve our research, but it's important that we test whether they actually do. So research improvement activities, things that are done that are meant to increase the usefulness of our research. And I think there's two things we want to be clear about, is whether these interventions can be effectively delivered, and then whether or not they actually improve research. And in our group, we've conducted both observational studies and randomized controlled trials. This is an example of two. The first is an observational study that we conducted in collaboration with the Nature Publishing Group. For any of you that have submitted a manuscript to any Nature Publishing Group journal will be familiar with that checklist that you have to say how you decided the number of animals you were going to use, were you blinded, how did you allocate to different groups. And what Nature wanted to know was whether that checklist actually improved the quality of reporting. It was a very active intervention because when you submit the checklist, the editors actually check the manuscript and would go back to the authors and ask for missing information. They had 4 key things they were interested in: randomization, blinding, sample size calculation, and exclusion criteria. So we did it before, and I think the checklist came out in 2012 or 2013. Can't remember off the top of my head now. But we did a before and after study. No studies reported all 4 of these things before. And even with this very active intervention, we got to 31 out of 181 that did it. And because we were starting with low, this is a highly significant finding. But, the raw numbers, I think, Nature were disappointed. They wanted to see a bigger effect. And then we also conducted a randomized controlled trial with PLOS, where we essentially, when authors submitted an article to PLOS One, they were randomized to being asked to either normal editorial process or being asked to submit an arrived checklist. And success was reporting of all arrived 20 items, and nobody did. And I want to just do a bit of a deeper dive into the Arrive study, because I think there's some interesting lessons in that. So the old Arrive had, like I say, 20 items, and these are the kind of the areas that it had the different sections in. So the study that we conducted with PLOS was called Icarus. I think the title showed that we were doomed to failure. But like I say, you submitted your article, you were randomized to just normal editorial process or asked for the checklist. You were only asked once, if I remember correctly. And then the articles that were published, we then assessed them using this web-based interface for reporting. But the way the Arrive guidelines or the checklist is written, the 20 items aren't 20 yes or no questions. So once we operationalize it, we end up with 101 questions that you could check for. We crowdsource the outcome assessment, and we trained the assessors, and each paper was assessed in duplicate, and then we reconciled the answers afterwards. So in terms of implementation, this is the number that were randomized, that went for peer review, that got accepted in the control and intervention groups. We were able to deliver the intervention. In the intervention group, we had 301 out of 340 checklists. So people, when they were asked to submit checklists, they submitted the checklist. That wasn't the problem. It's just that the checklist didn't result in better reporting. One thing that was interesting was that every paper was assessed by 2 people, and we had 8 of the questions in our assessment that had less than 75 agreement between the assessors, which suggested some sort of lack of understanding about what the questions meant. The lowest agreement, which was 49%, was for the unit of analysis. Is a unit of analysis for at least one test explicitly specified? And people just didn't understand what that meant. Despite being trained, despite having an explanation document alongside it, we might as well just tossed a coin to answer that question. And that study, that RCT, and then, like I said, we showed that there was no improvement, is one of the main reasons that ARRIVE was revised, and we ended up with ARRIVE, not just ARRIVE 2.0, but the accompanying exploratory and explanation document. So what the NT3Rs did, who are the developers of ARRIVE, is they established an international working group. And the difference between ARRIVE 2 and the first ARRIVE was that the first ARRIVE was only UK-based people who developed that. They established an international working group that include academics, members from industry, funders, journal editors, methodologists, and statisticians. They surveyed the international in vivo research community to gather how ARRIVE was understood and used. I think one of the big things about the original ARRIVE was that almost every journal endorsed ARRIVE, but nobody implemented it, and it wasn't having an impact on reporting. They ran a Delphi exercise with expert stakeholders to refine what the new ARRIVE would look like. And then they road tested it with researchers preparing manuscript to ensure that the guidelines are well understood for their main audience and fit for purpose. So now ARRIVE 2 is in 2 sections. It's got the essential 10, which is the focus for, I think, that we're going to use to assess whether this version of ARRIVE has been useful, and then the expanded recommended set. So it'll be interesting to see, and the plan is for an Icarus 2, although I think I might change the name in the hope that it's a more successful trial, to see how effective this has been. So I think I've come to the end. I'm just going to quickly go through some of the take-homes after talking for 50 minutes. So I hope I managed to share with you or convince you that in vivo studies which don't report simple measures to avoid bias give larger estimates of treatment effects. Most studies don't report these simple measures to reduce bias, although I think improvements are definitely happening. We generally work in silos with limited generalizability. Although I think I've done maybe 5 or 6 systematic reviews in the spinal cord injury space. And I think there probably is more collaboration in spinal cord injury research than I've observed in other disciplines. Reporting biases are important and prevalent. Most in vivo research is underpowered of unknown power. I think education will help, including training and critical appraisal. I definitely believe that interventions to improve reporting are far too late in the workflow. I think that's where a lot of energy has been. I think we should be thinking early on in the research workflow. There are some, I think, useful tools to improve the rigor of our research. But even as somebody who's active in this space, even I get confused about how many they are and what's the most appropriate one to use. Development and implementation is definitely going to require resource. I think it's important that we don't forget that, this is in its meta-science as a science, and research is required to determine how effective these interventions are. I suspect reward and incentives will likely drive change. And the key thing is remembering that any experimental design can be subverted, but what's important is knowing how to recognize when this has happened. Thank you very much for your time and for listening. This is my team. It's almost that dark now in Edinburgh, and it's only 4 o'clock in the afternoon. Thank you.
Thanks a lot, Emily. That was really interesting. We do have time for some questions. Dr. Lemon has posted a couple of questions in the chat. Anybody who wants to post questions in the chat is welcome to do so, or you can raise your hand and we can try to recognize you. Dr. Lemon, do you want to start with your questions?
Okay. So at the beginning, when you were talking about sample size calculations and that they're rarely reported, we do those, and we're required to do them by our IACUC. And so everybody who's doing animal studies, I think probably in the United States, if they have an approved IACUC protocol, they had to do some type of power analysis to justify the number of animals that they're using in their studies.
Mm-hmm.
And so we never report that in our papers that we did that, or maybe we have started doing it quite recently. I'd have to go check, I don't remember. But because that's like required, and I bet that's required in the UK, I'm surprised that that could not be assumed. I know that's not going to be true everywhere in the world, but it seems like that one, it seems. And so
that's interesting. So in the UK, our ethical approval process is slightly different in that we don't require approval at the experiment level. Your Home Office license is for a program of work over 5 years. And you have to estimate the number of animals that you will use. And you get statements. When I've looked at request forms, you get statements like, it's based on what we've done before. This is how, we generally use 6 to 8 animals per group. It's not necessarily a formal sample size calculation, one. I think the other thing as well is things are different in different jurisdictions. And we read research from different jurisdictions. And I think it's sample size calculation, I think power is fundamental to the rigor of an experiment. And I think it's so important. It's like, you can't do an experiment without ethical approval, but you can't publish a study without saying that your experiment had ethical approval in it. And I think it's that level. So I would push. And I think until people start reporting it, we also don't know the quality of the sample size calculations that they're doing, because I don't think they will all be of equal quality.
I think lots of journals are also and are encouraging people to use different types of data presentation where you're showing all the individual animals instead of a mean and a standard error or something like that. And so then you can really get a sense for what the variability, and that's
true.
You can postdoc do that on somebody else's paper, so but we'll start reporting that. Then my next thing was, we get negative findings or we get weird findings. Like we stumble on some technical thing that makes the experiment fail. And so like it wasn't even the goal of the experiment, and we can't get a result because of this weird technical glitch, some weird pH effect, or we're running into something. And so like we published a paper on this weird pH effect we had on AAVs. Now we have another thing that's going on. It's a lot of work. Publish a negative finding, and as you mentioned,
interesting.
and journals are not wild about it because it's not going to get a lot of citations, and their citation, they're impact factor driven. So my question is, if you want to publish a negative finding, would you consider RVX a suitable place to put that?
So I guess there's a difference between a negative finding because you've had a technical issue. I think it's different to accepting your null hypothesis, right? And
those are two different things. And I think we should be trying to publish negative findings for sure, absolutely.
Yeah.
But if we so to throw away my technical things and just say, a negative finding, is bioRxiv a way to go, or should we be aspiring to get it into a conventional peer-reviewed journal?
Well, I think they're mutually exclusive. I think the types of journals that, I don't think bioRxiv should just become a dumping ground for neutral and negative data. And I think there's lots of journals, especially journals that are very happy to publish pre-printed manuscripts that aren't impact factor driven, will accept those articles. I think the issue, I think, is probably more with us as researchers who, because it's not particularly interesting work to do, it feels a bit thankless, it takes a lot of time and effort, and like you say, there's little reward for it. And you're right, you're not going to get that study into a high impact factor journal. No, because they are impact factor driven. But there's lots of other journals that would accept, as long as it's a robust, you're asking an important question with rigorous methods, they will accept those papers. It's just, I think we maybe don't have the incentive to get them in. But putting them on as a preprint first, yes, but I don't think we should get into the habit of stopping there.
Thanks.
Jay, you have a question.
Thank you for that eye-opening talk, Emily. I want to piggyback on Vance's question. So obviously, it's obvious from your talk that when scientists are required to do something, they tend to do it, but when they're not required to do it, they usually don't. So the funding agencies have been adopters, right? And so they require us to do certain things or else we don't get the money. But it seems like, and I think you had a slide on Nature and then plus the PLOS journals as well. It's obvious that a big loose end in this whole process is that the journals don't require it, they recommend it. So, we were required when we submit the journal to Nature and their sister journals to submit things like randomization and blinding. But there's so many preclinical studies where they blatantly say we did not randomize and we did not do this in a blinded fashion, but it gets published anyway. And so then then the journal just kind of shrugs their shoulders and puts all the onus on the authors. It's more like a social media platform where all the content providers are really the ones, quote unquote, responsible for all this. And we tried our best. What has been your experience when you're dealing with journals for requiring these things for publication?
So you raise two really good points there. So with the requirement issue is complex. And when I think about our ICRA study, the amount of resource it took to assess for whether these things were reported was huge. These aren't, and I think that's part of the issue, it's just simple manpower to look for these things. And Nature obviously has lots of in-house editors, and they spent a lot of time checking for these things, which is why you then now have these articles that say I didn't do it, because they're focused on transparency. It's about understanding what people did and how they did it, rather than telling people they should do it a certain way. I think part of the hope is that if you force someone to say I didn't randomize or I didn't blind, they only want to do that once. They don't want to have to write that in every single paper that they publish. So that I didn't randomize, I didn't blind, I think personally, is better than having nothing written there, because then I'm clear. It allows me as a consumer of the research to really understand how robust it is. And that is, it isn't that robust. But in terms of the investment that's required to really enforce this stuff, and part of our PLOS study, there were a whole load of feasibility outcomes that we had at PLOS. And the time it took to properly assess whether a paper was appropriately reported is yeah, almost impossible. I think the journals, to be honest, my experience of working with journals, and I'm slightly biased because I'm an editor-in-chief of a journal, and I collaborate with journals, but the fact that they've invested that resource for these collaborative research studies to try and improve their reporting, I think is a sign of good faith. It shows that I think they're invested, they think this stuff's important. I think given how much money goes to publishers, I think we should maybe be, I don't know if the States is in the same fights that we have in Europe with some of the big publishers and, you know, their profits. But I think some of that money, you know, could be being invested in resource to support enforcing. Because right now there just isn't that resource to be able to actually check. Because to enforce it, you have to check it rather than just say, which is why they've stopped short of enforcing, essentially. I don't know if that answers your question, but I hear your frustration.
So I guess we could have one more. If there's a pressing question, we could have one more. I'm going to save mine because I'll be seeing Emily in a minute. So any questions? Okay, if not, I will thank Emily again for a great talk. And I'm sorry that you couldn't come to real Miami, but thanks for coming to virtual Miami.
Thanks for having me. And thanks everyone for being here and listening.